Hello students, so I'm back here with the next session of IOQP. So guys, today we are going to do something which is related to what we did in the last session. In the last session, we covered variable mass systems, and one of those systems is chain. So today we are going to deal with some chain related problems. All right, so let's start doing it. So I will first tell you the flow of the session. So I will tell you the answer to the teaser question that I shared in my last session. So we'll begin with that. Then I'm going to show you the question that we are going to cover in this session. Then I'm going to show you the answer to that question so that you can just pause the video at the question, you can attempt the question, and then you can check whether you were able to get the answer by yourself or not. And then we are going to see the solution of the question that I'm going to discuss today. Today I'll be discussing only one question because that will suffice. That will have 4 or 5 parts, and that would be a good enough number of parts to cover all the aspects that I want to discuss today. And finally, I'm going to give you teaser questions. So today I'll be providing you 2 teaser questions. And along with that, there is one thing that I would like to ask to all the students, one conceptual thing. So let's see how many of you can answer. So let's begin by discussing the last teaser that I shared in my previous session. Okay, so this was the question that I shared, and we sought solutions from the students. We asked the students to send their solutions on this particular email ID that you can see on the screen right now. I'm happy to receive some solutions, like approximately 8 to 9 students sent their solutions to us. We went through the solutions. One of my colleague, Chandan sir, who is a specialist for Olympiad batches, he checked all those solutions, and I also checked some solutions. So some of you would be getting replies from Chandan sir, and I would like to present the correct answer here. So something of this sort will be the answer, and I would like to mention 2 students in particular who sent their solutions to us. So Tushar solution was the best among the lot. It covered all the different cases that are possible. It I like the fact that Tushar covered one of the case that did not even occur to me. So I'm pretty happy with that, and I want each one of you to see Tushar's solution. I'm pretty sure those who are curious enough will definitely want to see what he sent to us. So what I'll be doing, I'll be presenting Tushar's solution in the form of a PDF in the description of this particular session. So Tushar, please forgive me if you feel that I'm taking liberties in presenting your solution to the other students. I hope you don't mind that. Uh, and Kritant also did a very good job. Kritant did send the correct solution, but the solution was not a comprehensive one, but he still did a very good job. And for the other students, the thought process was nice. For some it was incomplete. So I think you will probably receive a reply from Chandan sir. So guys, that was for the previous session's teaser. Those of you who are looking for the correct answer, just check Tusar's solution. It is comprehensive, it is easy to understand. All right, and I'm pretty sure that you're going to like the thought process. So let's begin today's session. So this is the question that I'm going to cover in today's session. You can have a look at the question. The question is not complete here. Only one part of the question is present here. The remainder of the question is on the next slide. You can click a snapshot of this, and this is the remaining of the question. So what you can do, you can pause the video now, and you should attempt this question all by yourself. So this is what you should do. Assuming that you have paused the video and now you are ready with your answer and you want to know whether you got the correct answer or not. So I'm going to show you the correct answer. Okay, so 2 parts of the question were still on the third slide. So these 2 parts, if you haven't attempted yet, please do so. Pause the video now, attempt these 2 parts, and then you can come and check the solution answer. I mean, so these are the answers. These are the answers to all the 5 parts, and the 6th part asks you to make a graph. So the qualitative nature of the graph would be like this. The red line that you are seeing, the red curve that you can see on the screen, this would be the shape of the curve that we have to draw. All right, so I hope that many of you got the answer by yourself. Those of you who could not, no worries. Let's attempt this question, and then when we are going to have a look at the teaser question. So Here is the question, guys. I'll begin by reading the question. A chain of length L and linear density lambda hangs from a horizontal support with both ends A and B fixed to a horizontal support. So I think it's pretty clear from the figure what they are speaking about. So there is a chain and the two ends of the chain are fixed at point B and A. Okay. Now the two ends are fixed close to each other. This is a very important statement to mention in the question, because if these two ends are finitely distant from each other, if the distance is not negligible as compared to the length of the chain, okay, then the physics of the question will change. Like, it will not only be a mathematical change, the physics will change. Okay, if these two ends are distant, then energy is conserved, and if these two are very close to each other, then energy losses take place. So this particular situation is a situation in which an inherent loss of energy takes place, which is quite difficult to understand unless somebody explains. So let's see if we can discuss that aspect also. So at t equal to 0, the end A is released. So we release one end, so it starts falling. All vertical distances are measured with respect to the horizontal support with downward direction. All right, so I'm pretty sure that you have read the question. Now I'll now begin presenting the solution of the question. So the part A of the question says that we have to obtain the momentum of the center of mass of the system when the end A has fallen by distance x, it should say, in terms of x. And so this end has fallen by a distance x, so this is x. And what we want to do, we want to express the momentum of center of mass of the system. So momentum of center of mass of the system basically means that we want to express the total momentum of the system. Okay, so let's see how we are going to do that. So I'll begin by giving you some arguments. You tell me whether you buy those arguments or not. That means you agree with me or not. So my first argument is that this end is probably traveling at some speed. Okay, for now, let's just call that speed as v. Okay, I guess you all agree with me that this end is falling. So obviously, by the time it has covered some distance x, it must have acquired some speed v. All right. Now my next argument is that choose any general point here. Let's call it as p. So my next argument is that p at this particular instant is also falling with a speed v. Now tell me whether you agree with this or not. Pause the video here for a moment and think about this, whether this is logical to think, it's intuitive, or can we present an argument for this claim. Okay, actually you should be able to present an argument. You know, intuition is good to give you a direction of thought, but then that thought must be backed by mathematical evidence or some kind of logic. So I'll tell you what my logic would be. My logic would be that I'm treating the chain as an inextensible piece of rope with mass. Okay, since this chain is inextensible, therefore the distance between point A and any fixed point P on the chain should not change. That means that the approach velocity between these 2 points should be zero, which basically means that if this point A is having a velocity v in the downward direction, okay, then all these points of the rope should have the same speed v in the downward direction. So that is my argument. But this argument is true for what all points? Let's try to figure out. So all these points, yeah, all these points which are on the right side of the rope, okay, I would say that they are traveling with speed v. Now, what is happening to the points which are on the left part of the rope? Let's see that. So this topmost point B is at rest. So the velocity of point B is 0, which means that the velocity of this point is 0, 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 and so on. All right. So I think we are reaching a point where some doubts or some queries would be popping up in your brain now. The left part of the chain is having zero speed. The right part of the chain is having speed v. And this seems logical. Where we are going to face difficulty is where we are approaching the same point from both sides. All the points on this side have speed v, all sorry 0. All the points on this side have speed v, and we are approaching towards the same point. So what about the velocity of this particular point? So guys, here is something going on here at the small segment, at the segment of infinitesimal length at the bottom. Something is going on where lies all the discrepancy, or you can say the answers to all the discrepancies. I told you that if the two ends are separated by finite distance, then the falling process of the chain is the one in which energy remains conserved. Okay, and if it's too close, what is happening here? Let's try to understand. If it is too close, then there would be some elements or some entities with masses that would be coming to rest abruptly. Okay, and there lies the loss of energy. If any entity with mass is traveling and if it is coming to rest suddenly, then this process or this event is equivalent to a collision, because collision is what? Collision is nothing but an event in which velocity changes suddenly. That is a collision. Okay, so so I think we should finish this part now, because uh, I'm pretty sure that many of you now agree with me that the left part is having zero velocity and the right part is having velocity v. And whenever we are trying to write the momentum of a system, we basically look for this equation like m1 v1 plus m2 v2 and so on. So basically what we do, we consider all the masses of the system or all the particles of the system, we consider their velocities, and we multiply the mass with their velocity, respective velocities, we add them up and we get. So if I talk about this entire part of the chain which has a length of how much? Well, can I say that the length of this part is L by 2 plus X by 2? Think about this. If this end has fallen by a length L, if this end has fallen by a length X, I'm sorry, all right, then half of this X comes here, so this part is X by 2, and half comes here, this part is X by 2. So this is the length of the chain that has fallen. Half goes here, half goes here. Okay, so the length lying on the left side is L by 2 plus X by 2. The length lying on the right side is L by 2 minus X by 2. So my claim now is that this particular length, which is L by 2 plus X by 2, this length would have a mass of this much length into the linear mass density. Okay, and it has a velocity of 0, and at the same time the other part of the chain, which has a length of L by 2 minus X by 2 into lambda, has a speed v. All right, so the overall momentum would be lambda v into L by 2 minus X by 2. So this should be the answer to the first part, which says that the momentum of the center of mass of the system, okay, when end A has fallen by a distance x, should be here in terms of x and speed v. All right, so I think this should be the answer. Now there's one more thing what we can do here, like I think this qualifies to be called as the answer for the first part. But what about the speed v of this end A? Can we talk about this? All right, can I say that end A is falling freely, and hence after having covered a distance of x, the end A will have a speed of root 2 gx? Can I say that? Can I say that? If you have just agreed with this, okay, then you can pause the video here and you can think, why did you agree for this? Why did you agree for this argument? Is it because just I said so? Think about this. This is my first teaser for you. Why we should consider this end to be falling with a speed, to be freely falling? Why should we consider that? Considering that is right or not, that is my first question. Assuming that it is right, which is right, okay, what is the justification for this? Because I don't see that it will fall freely. I have a counter argument for this. I think that end A is connected to the remainder of the chain, and there may be some tension at this end which will make the acceleration of this end more than g. Okay, so can we refute this argument? Can we find something can a counter argument for this? Think about this. This is my first teaser to you, and especially you should address this teaser if you agreed when I said that we can consider this end to be falling freely and this end to have a speed equal to root 2 gx. If you agreed to that, then pause the video and ask yourself, why did you agree to that? You shouldn't have, unless you find the reason for that. All right, all right, so this is the answer to the first part. Let's just go back quickly and check whether this answer is correct or not. So here I can say that yeah, this part looks correct. Okay, now let's move to the second part of the question. So second part says that assume NA is falling freely under gravity. Okay, so here in this particular question, the question is set to assume that, all right, which again brings me to the same question. Is it an assumption? And if it is it a valid assumption? Think about this. Send me your arguments for this. Okay, the acceleration of the end A equal to G as obtain tension at the fixed end just before the chain completes the fall and becomes entirely vertical. So what I'm going to do, we obtained the momentum of the chain, and that momentum was lambda into L by 2 minus x by 2 into x, which was into V, which was this. Now, can I say that the net force acting on the chain will be equal to the rate of change of momentum of the chain? So that is what I'm going to do. I think I can draw the FBD of the chain, of the falling chain, somewhat like this. I can claim that there is a tension here T, and there is an mg here somewhere here, and I can write this equation that mg minus t is equals to dp by dt. Remember, this p is assumed to be in the downward direction because all these particles were having a downward speed. All right, so lambda into L will become the mass into G minus T is what we seek, is equals to time derivative of momentum. So what I'm going to do, I'm going to write lambda here, root 2G here, because these are all constants. Okay, and then I can consider L by 2 along with root x. So L by 2 derivative of root x would be half into 1 upon root x. I hope I'm doing everything okay. Looks like that, into dx by dt, which is v, minus, now this x by 2 will be multiplied with root x, so we will have a half into derivative of x raised to power 3 by 2. So 3 by 2 will come in the front, x raised to power half, that means root x will be there, and then derivative of x is v. So this is what we should be getting, and now I can see, I can simplify it as much as it is possible. So one thing I can notice is that we can bring out the V as it is present at both places. We can probably bring out 4 also. Okay, so 4 here, V here, and what we are left with is L by root x minus 3 root x. This is what we are left with. Okay, now we can find tension as a function of x also, but part B is asking me to find the tension just before chain completes the fall. Now what does it mean that the chain completes the fall? It basically means that the chain has straightened. So chain becomes straight when the value of x becomes equal to the length of the chain, which is equal to L. So I'm simply going to substitute L in place of x. All right, so we are going to get, let me switch the slides. So lambda root 2g into v by 4 is what we were getting. Mg minus t was equal to this. Let me just go back and check. And then we will have L by root x minus 3 root x. All right, so lambda root 2g into root 2gx, which will turn to L. So root 2gl by 4 into L by root L is root L minus 3 root L. So we are now left with lambda into 2g into root L. Root L and 1 root L will come out also, so it will become L by 4, and here it is minus 2. All right, so we are left with minus lambda GL. So if you ask me the value of tension, it is mg plus lambda GL, which is same as 2 times of mg. All right, so we are getting that once at the instant chain would be completing its fall, the tension at the other end, the end which is still suspended from the ceiling, the tension at that end would be equal to 2 mg. Let's just go back and check. So I guess this part is also correct. All right, I hope you got the solution. I hope you understood the solution. So let's move to the third part now. Okay, I think the third part is mentioned in this slide only. So the third, okay, there's something interesting mentioned here. The value of tension is found to be different from the above result. All right, so there is something here that we have considered, which is part of theory only, which does not play a role in practical life. Okay, so let's try to find an alternative approach, and let's try to see what we can do. So option or question C says Obtain the potential energy of the chain and plot it versus x. Take the potential energy of the point mass placed at the horizontal supposed to be 0. So what we are supposed to do now is that this is the initial shape of the chain hanging from the ceiling, and then let's say we released one of the ends and it fell by a distance x. Okay, it fell by a distance x, so this length would be x by 2 and even this length would be x by 2. So considering zero gravitational potential energy here, we have to write the potential energy, the gravitational potential energy of the chain as a function of x. Let's try to do that. So what I'm going to do, can we consider this as a straight rod, the center of mass of which would be somewhere here, and this again as a straight rod, the center of mass of which would be somewhere here, and this curved part can be ignored and it would be very, very little in size. So let me consider this to have a mass m1, this to have a mass m2. All right. So we can begin by writing the masses. So m1 would be lambda into L by 2 plus x by 2. Check this. Similarly, m2 would be equal to lambda into L by 2 minus x by 2. Now, what is the distance of m1 from the ceiling? What do you think, guys? What do you think is the distance? The distance of m1. So if m1 is the center of mass of this straight segment, then it should lie at the midpoint. So the I can say y1, this distance. Okay, so y1 would be given by half of this length, which is L by 2 plus x by 2. So it becomes L plus x by 4. All right. So I've written this length. Now consider that if we are consider like keep in mind that if we are considering this as zero height, anything that lies below this will have a negative gravitational energy. All right, so keep that in mind. So similarly, y2 would be equal to this distance. Now, how can we write this distance? So we can write this distance as you can say this entire length, which is x, plus half of this. Half of this length. So y2, let me write y2. Y2 would be x plus half of this length. And how much is this length? This is L by 2 minus x by 2. Okay, so it eventually becomes what? It becomes L by 4, L by 4 minus x by 4 actually. L by 4 minus x by 4 plus x. So it becomes L by 4 and plus 3x by 4. Okay, now the gravitational potential energy would be written as minus m1 gy1 minus m2 gy2. So just do the substitution and you will get the answer. So it will be minus lambda into L by 2 plus x by 2 into y1. y1 is L plus x by 4 into g, and then minus lambda into g into actually lambda and length L minus x by 2. This m2 I have written, g I have included, y2 is there. So y2 is L plus 3x by 4. All right, so we now need to simplify this. Let's see how much we can simplify. So u is equals to, what I'm going to do, I'm going to write minus lambda g as the common entity, then 4 and 4. Here we have 2, right? Do we have 2 here? Yeah, here also we have. So 8 can be taken out as common entity. Anything else that we can take out as common? No. So then we will have L plus x square minus, no, it will be plus only because minus we have already taken out. L minus x into L plus 3x. Have a look at this, guys. All right, now we just need to simplify this. So minus lambda g by 8, and then we will have L square plus x square plus 2xl plus L square plus 3xl, L square plus 3xl minus xl minus 3x square. So we will end up getting lambda g by 8, and then we have L square and L square is 2L square. X square and minus 3x square is minus 2x square. And then we will have 5 minus 1, so 4xl. So we can pull out 2 as the common quantity, so minus lambda g by 4, and then we have L square minus x square plus 2xl. So that becomes potential energy, gravitational potential energy of the chain as a function of x. Now let's have a look whether this is correct or not. So I guess we got this only, minus lambda g by 4 L square minus x square plus 2xl. All right, so all good till now. All right, so we have obtained this part also. Now obtain speed v when end A has fallen by distance x. Assume that all the sections of the falling part have the same speed. Now they have asked us to assume this. We did this in part A also. So let's continue now. Now that you have found out the value of U, we are now in a position to use energy conservation, assuming that it is applicable. Okay, that is what the question wants us to do. So Ki plus Ui, that means kinetic energy plus potential energy at the initial state, is equals to Kf plus Uf. So conservation of mechanical energy is what I'm trying to use. So initially the entire chain was at rest, so Ki would be 0, and initially the chain was simply hanging like this. All right, so the center of mass chain would be somewhere here, and this length was L by 2, which basically means that this would be L by 4. So I'm going to write minus into mass of chain into G into minus L by 4. So that's Ui. Now Kf we can write as half into only the falling part. Like we have to consider the mass of this part only. Okay, because we know that all these points are at rest. So if this end is going down with the speed v, the mass of this part, I'm going to write this as lambda L by 2 minus x by 2, because we know that this length is L by 2 minus x by 2. Okay, so half into m into v square, okay, is the what kinetic energy is. And uf we just obtained that, so minus lambda g by 4 it was. And then we had let me just go back and check, it was L square minus x square plus 2xl. All right, so this is what we have to simplify now. On left hand side we have plus lambda g L square. Actually I used minus sign twice, so let me just change it to plus. So in that case this will become this will become minus, yeah, okay, is equals to next we are going to write lambda v square by 4 into L minus x minus lambda g L square by 2. I'm expanding this bracket now by 4 actually, and then plus lambda g x square by 4, right, and minus lambda xl by 2. G is also there. Okay, so in these terms I see only this term getting adjusted with this term, and we want to find v, so let's take everything on the other side. So when this comes on the other side, we are left with minus 3 by 4 lambda g L square, because this will become plus 1 by 4, yeah. And then we will have minus lambda g x square by 4, and then we will have plus lambda g xl by 2 is equals to lambda v square L minus x by 4. Okay, so eventually, okay, I have run out of space, I think. Okay, anyways, I'll solve it here. Uh, what? So this will become, I can write lambda g by 4 2xl 2xl, and then uh, minus x square, and then minus 3l square. Okay, so I've written this part entire thing into 4. Okay, 4 is on both the sides, so this 4 gets cancelled. Okay, and then we have lambda into L minus x equals to v square. So v is coming out to be root of lambda g, lambda also gets cancelled. Yeah, lambda also gets cancelled. Okay, so we will cancel lambda also. Lambda gets cancelled. Okay, so g into 2xl minus x square minus 3l square divided by l minus x is what we will get. Now, time to check whether this is correct or not. Let's go back to the answer slide. And okay, I think there has been some error. All right, guys, found the error. So when I wrote this quantity here, I omitted the 4. Okay, and once we do that, this entire thing gets cancelled, which means this term will not be there, which means we will not have a term of 3l square. Okay, so I think it was a slight calculation mistake on my part. Pardon me for that, guys. And now if I check the answer, it seems to match. Root g 2lx minus x square upon l minus x. So do we have that? Root g 2lx minus x square. Yeah. So now we have got the expression for v also. Okay, and we have simplified. Okay, now this was the answer to the part D. Okay, now part E asks us to obtain Tx at B as a function of x. So tension at B as a function of x and related quantities we want to find out. We are advised to simplify our expression as far as possible. All right, so how do we do this task? What we are going to use here? We have used the energy equation to obtain the value of speed, and the speed was root g into root of 2xl minus x square by l minus x. Now what we are going to do, we are going to write the expression for momentum again. Okay, we are going to write the expression for momentum again. Remember that in part A, we wrote momentum in terms of V. Okay, and we are going to do that. So lambda into L by 2. Okay, lambda into L by 2 minus x by 2. This is mass into velocity is root g root of 2xl minus x square minus l minus x. So this becomes the momentum of the falling chain now, and the remaining steps will be same. So let's see how we do that. All right. So I'm again going to write mg minus t is equals to dp by dt. Now, these steps are going to be a bit long, and this is something that you all can manage on your own. So what I've done, guys, I have done this calculation already, and it is present with me. Instead of doing the entire calculation here, which can be a bit of time consuming, and boring for you guys also, because I know that you are watching this session probably as a replay. So I just walk you through the steps. Ideally, you can pause the video here, you can do this calculation, and you can find the answer, and then you can just move ahead in the video and see what you are getting is what is correct or not. Okay, but if you want to have a look at the steps, I'll help you with them. So we have this is the printed solution. So we obtained u, we obtained v, and we are now at this stage. We have just now written the momentum, and now we are differentiating the momentum. So lambda root g and 2 is here, and then we have taken this l minus x inside the root. So l minus x in the denominator gets cancelled, and this is what we are getting. Next, we keep this term as it is, and we expand this part. So we are going to get 2l square x, the multiplication of these two, then minus 2lx square, that is the product of this and this, then minus x square l, the product of this, and finally plus x cube, the product of these three. So this is what we are going to get, and now we can we can just combine these two to write minus 3lx square, and now we are in the differentiation step. So this is simply copied from here, and then we have a half. Then since the power it has a root here, so it comes in the denominator, then derivative of this entire expression is written here. It will become 2l square minus 6lx plus 3x square. All right, and now since we have to differentiate with respect to time, but till now all the differentiation was done with respect to x. So finally we have to multiply with the dx by dt also, which is nothing but v. So notice that this entire expression is nothing but speed. Okay, after simplification, once this is done, rest is simplification only. All right, so you just simplify this, and like you can take out one x as the common quantity here, and once you simplify, this is what you are going to get. Okay, so this derivative is mg minus t. So again you simplify this, keep on simplifying, and you obtain tension as a function of x like this. All right, so this is what we are getting now. In part B, we found out the value of tension using the momentum method when the complete chain has fallen, and we obtained the answer as 2 mg. Okay, now if I consider the same situation when x becomes equal to L, I see that tension in the string becomes infinite. Okay, now this is certainly not the case, because this certainly doesn't happen. We hang a chain, we release one end, the chain falls. If at all the tension becomes infinite at the end, which is fixed to the ceiling, then all the materials should break, irrespective of whether the chain is of iron or whether it is of any other material. Infinite tension, so the chain must break. But it doesn't happen that way, right? It doesn't happen with threads also, chains also. So definitely something that we have assumed in this solution is not what happens in theory. Okay, some gap is there, right? So where is the gap? So guys, we did energy conservation here. We did energy conservation here, but energy conservation is not applicable because as I told earlier also, in a falling chain, what is happening, all these ends are having some zero velocity, and all these points are having a velocity, a downward velocity of v, and in the next dt duration some additional part will come to rest. All right, so what is happening basically, if I tell you that in next dt duration this end would have fallen by a distance of v dt, and out of this v dt half of the length would have come here, so v dt by 2, this much length would have come here, and the remaining would still be here. So this v dt by 2 length would have come to rest suddenly. Before dt time, this dm mass was traveling with the speed v, and after dt time, which is the negligible time, in negligible time this mass has come to a sudden rest. So the situation is equivalent to the case when this mass underwent a collision, and therefore the loss of energy. So all right, we accept that this particular solution or this particular assumption that the energy is conserved may not be correct. I hope you buy this argument now, you agree with this. But what was wrong with the first solution? The question said that practically, experimentally, the value of tension is found to be different from the other result. So what is wrong there? So what is wrong there is that we assume that the two parts are extremely close to each other. Now again, this extremely is not defined. Like mathematically it's negligible, but practically when you hang a chain, there is always some distance. All right, and what actually matters is the size of the linkage, as compared to the horizontal distance, because consider this linkage will set a minimum limit on the separation, or this actually affects the entire solution. This is what we have ignored in our solution, but practically it is present there. So therefore the difference. I hope you like this question. I hope you understood the subtleties of the two methods and why both the methods fail to match with the practical result. Okay, with that thought guys, I will now leave you with teasers, and there was one part where we assume that this end is freely falling. The question asked us to assume that. We did that also. That is true also. Let me tell you that is true also. But why? How can we prove that, or what argument can we give to prove that this end is indeed falling with the acceleration g. My counter argument is this end is not a isolated entity. It is connected to a heavy chain. There can be tension in chain. Since it is heavy, the tension can be variable at different points. So there can be some tension here which will make the acceleration of this entity more than g, because it will be acted upon by mg also. However less the mass is, it will still have some weight and some non-zero tension, so the acceleration will be more than g. That is what I think. Can you prove me wrong? I am wrong. Can you find the logic behind it? That is my first teaser. Send your arguments to support how the acceleration of that end can be proven to be g. And apart from that, I'll show you the graph. You can plot this graph. I'm not going into how to plot this graph. That depends on your mathematical skills. I'll leave you with two questions related to chains. The first one is that you can see on the screen. I hope you can attempt this. Send us the solution for this question. This question also involves the fact that the top end of the chain would be falling with an acceleration of g. All right, so explain that aspect. And the other question, the second question, which you can see on the screen right now, is a derivative of the question that I covered in the session. It matches closely with what we covered in the session. Yet I would like to see how you present your answer. All right, so do send us your solutions at this particular email ID that you can see on the screen. I will particularly encourage the students of 9th and 10th grade. Of course, these topics are something that you do not cover at your 9th and 10th grade physics. But I'm assuming that there are some physics enthusiasts out there who prepare for Olympiads at a very young age. And I'm hoping that some of these enthusiasts are watching this session and they are quite interested in letting us know how you think, how you present your answer. So do respond, guys. And it was fun doing this session for you. I'll be bringing more such sessions. Stay tuned, guys, and keep coming back to watch the videos here, and do subscribe our channel. Thank you, guys. Bye bye and take care.